Chapter 3, Exercise 4. Show that there is no set to which every ordered pair belongs. So this question is pretty standard. It's nothing we haven't done before. At this point, it's just showing that if you were to construct a set to which every ordered pair belongs, you would construct a set to which every set belongs. And then, everything falls apart, math breaks down, we divide by 0, and the world ends. So we don't want to do that. So we want to show that that is indeed impossible. And I was wondering why this wasn't just a corollary to the definition of ordered pairs, why this needs to be an exercise explicitly. And then I remembered that every single time I am asked to show that there is no set of all sets, I kind of stumble, and it takes me a while to recall how to do the proof, if at all. Sometimes I just need to reference the text or something to remind myself how to even start it. So in a way, I think it's important to just learn this information, and then the more you do it, eventually, hopefully at least for me, I'll someday memorize it, and then I won't have to reference the text every time. I think it's also important to just make these facts very clear, and there's no way to make them clearer than to just prove them yourself. I think that's how I retain most information. Whatever I read, whatever someone else wrote, at least in terms of math, is not quite as memorable as the exercises I've worked out on my own, which is honestly the whole point of this YouTube series of me just solving these exercises, because one, it forces me to actually do the exercises if I want to post them every day, and two, it forces me to explain my thought process and not just write some shitty proof that no one understands but me. And if no one understands your proof but you, then you probably don't understand your proof yourself. That's one thing I've learned after doing math for so many years. Anywho, it's a lot of preamble, so let's just show that there is no such set. And what we're going to do is we're going to assume to the contrary that such a set S exists. Right? So, in particular, for all A comma B, every ordered pair A, B is in the set S. Right. So one way I believe that this falls apart is, where exactly are you getting your A and B from? So if you ask that question, then you can just say, oh, you're just getting them from the set of all sets, which is just, or the class of all sets, and that kind of just makes everything fall apart in my opinion. You don't need to elaborate much more. But there is a rigorous way to prove this. It does rely on understanding how exactly the ordered pairs are constructed, though not too much in detail. Or rather, it changes the details of how we're going to approach this a little bit, depending on how exactly you define your ordered pairs to be. I'm going to use the Kuratowski definition, which is the one that is presented in... Did I write this properly? Give me 1 second. Let me just find the book. I think Kuratowski was Polish. 1 sec. Yeah, it looks like a very Polish name. I'll look it up after the video's over. Yeah, I wrote this properly. Or did I? Sorry, I don't trust my eyesight. I just kind of eyeballed it. I didn't read it too carefully. Kuratowski. Yeah. Okay. So there it is. So Kuratowski's definition is that the ordered pair A comma B is equal to the set of the set containing A. Sorry, that's muscle memory. The set containing A and B. Right? So, okay. So what does this mean? This means that in particular, that for all A, for all B, then this set, which is just equal to our ordered pair, is going to be an S, right? This leads to the fact, getting more elaborate with my transition sentences, that the set containing A is in the union of S, and the set containing A comma B is in the union of S. Why? Because this is in this, and this is in this, right? I won't go into too much detail. That's all of chapter 2. Okay. And then it follows that A is going to be in the union of S, and B is going to be in the union of S as well. And more specifically, for all A, for all B, or rather, let's split these up. For all A, this is true, and for all B, this is true. Okay, so there you have it. For every set A and every set B are in the union of S, so we've created a set of all sets, which is, again, a big no-no. Now, that's enough, in my opinion, since we've proved it before, that we can just appeal to the fact that there is no such set of all sets. But let's just go through the proof once more, because I think it's useful, and hopefully this time it will eventually actually stick in my brain. So, in particular, A, which is going to be equal to the set of sets X, such that X is not in, or rather, X in the union of S, such that X is not in X, right? And this is the standard kind of self-referential paradoxical set that you construct. Then, if, or rather, I'm just going to write it logically. So A is in the union of S, right? And or rather, since A is in the union of S, if A is not in A, then A is in A, which is weird, right? And then similarly, if A is in A, then it satisfies this condition, right? If A is in this set, then it satisfies, then A is in the union of S, and A is not in A. So this is equivalent to saying that A is not in A implies that A is in A, which implies right back that A is not in A. So A is in A if and only if A is not in A. So yeah, you have probably about as pure of a contradiction as you can ever come up with. That is something being equivalent to the negation of itself, which, if you've done logic, or if you probably think about this for like 10 seconds, is not possible in any way, shape, or form. So our only resolution is that A is not in the union of S. Alright, if S is indeed a set. So the set containing A is not in the union of S, and A comma B is not in the union, is not in S for this specific A, right? It just kind of propagates back up the chain of command. Thus, S cannot, or rather, S does not contain all ordered pairs. And there you have it. It's just kind of unwrapping the definition of ordered pairs and then showing how that leads you to a contradiction, because we assumed that there is a set of every ordered pair, and then now we show that S does not contain every ordered pair. So that's a contradiction. About as straightforward a contradiction you can find. So yeah, there you have it. That's it for this video. That's it for the set of all ordered pairs. Probably never going to see this again. So I hope this was helpful, and I will see you in the next video. Bye bye.